Hey math fans, Alex here, and in this lecture we're going to start 1.2. But before we start 1.2, I want to go back to a question that I asked last time in section 1.1, which was de Meur's paradox. So essentially, if you roll 3 dice and take the sum, it's more likely to get a sum of 11 versus 12. And de Meur argued, well, wait a minute, they should actually occur with equal probability, because rolling a sum of 11 can occur in 6 ways, which are enumerated below, and rolling a sum of 12 can also occur in 6 ways. So what is the deal? And I asked you to kind of think about that. Well, here's kind of the solution, so to speak, of this paradox. And it's actually, I made a tiny lie when I said that rolling a sum of 11 can occur in just 6 ways. Now, these six ordered triples of numbers are the only such combinations that will produce a sum of 11. But for each of these ordered triples, I could rearrange the numbers in such a way that I also get a sum of 11. Okay, so then the question becomes, well, 6, a 4, and a 1, well, how many different ways are there to arrange the 3 numbers and still get a sum of 11? And the answer actually doesn't really matter. We'll explore that in this lecture, but what does matter is the fact that you're going to get a lot more possibilities with 3 distinct numbers versus numbers that repeat. Okay, so if you look at this ordered triple has 3 distinct numbers, this one has 3 distinct numbers, and this one has 3 distinct numbers. And if you look at rolling a sum of 12, that also has 3 ordered triples with all distinct digits, right? This one, and this one. So however you rearrange, whatever the answer is to how many ways you can rearrange them, these are pretty even, right? They kind of cancel each other out. So far, we're tied. Getting a sum of 11 is tied with getting a sum of 12. However, with the ones that repeat a digit twice, we're also tied because 2 of them, that one has a repeated digit, and that one has a repeated digit. Well, this one has a repeated digit, and that one has a repeated digit. It's not until you go to these last ones that you really see the distinction. And that is the answer that Blaise Pascal proposed to de Meur. Blaise Pascal was a French mathematician of the 17th century. He said, well, look, 4, 4, and a 4 can only occur in one way, and a 4, 4, and a 3 can occur in 3 ways. Okay, so that's why B is less likely to occur than A. And that's kind of the solution to de Meur's paradox. Alrighty? So, this lecture is entitled Rudiments of Combinatorial Analysis. And while those are a bunch of big words, hopefully I can break that down for you. This is going to take many lectures to cover section 1.2, just because it's very important. So our objectives are to use combinatorics to calculate n and n of a in various circumstances. So we know that probability, if you'll recall, the formula for probability was n of a divided by n. And I said this is a deceptively simple formula, but these numbers, calculating these numbers in a variety of situations, that's going to be the tricky part and what we're going to focus on. Okay, I also want to connect ideas behind subpopulations and partitioning a population to ideas that you might have heard of in high school math, mainly combinations and permutations. I also want to use Stirling's formula to approximate n factorial for large n. And we'll, of course, review the factorial notation. All right, let's jump right in with a theorem. This is going to allow us to start counting. So, Theorem 1.1 says the following. Suppose that I'm given n1 objects, which we're going to label A1, A2, all the way up to A sub n1. And we're given n2 objects, maybe call them B1, B2, all the way up to Bn sub 2. So if we have that situation, then there are exactly n1 times n2 distinct ordered pairs of the form a sub I and b sub j, where I is either 1, 2, all the way up to n1, and j is 1, 2, all the way up to n2. So it's basically saying if you have a group of objects, they don't even need to be numbers, but any group of objects, you can enumerate them, 1, 2, 3, 4, all the way up to some n1. And if you have a second group of objects, maybe colors or something, you can enumerate those. Then there are n1 times n2 different combos, pairs of those objects. Okay, so hopefully that makes a little intuitive sense, but we're actually going to prove this one. Okay, so to prove that, we're going to go ahead and let the n1 objects or elements be distinct. And then we will assign each of the objects a1 or a sub I, we're just going to have that correspond with the number I. That way, instead of thinking in terms of objects, we're really thinking in terms of numbers. So if you have like the colors of the rainbow, red, orange, green, blue, indigo, violet, you can just replace red and call it 1. And orange is 2, right? You can just replace them with the numbers, and then this is a little easier. Okay, and of course, b sub j is just going to be paired up with j. This is really a bijection if you're familiar with group theory, but nonetheless, since I ranges from 1 all the way up to n1, and j ranges from 1 all the way up to n2, and these are numbers, we can plot all the ordered pairs, right? We can plot, AI, bj. We can plot all of those systematically by corresponding this with ij in an xy plane. So just plot all the different combinations they could be. And when we do this, how is it going to look? And we have all possible ordered pairs, right? So we're going to have an ordered pair at 1, 1, at 2, 1, etc. And you have this lattice. And the object of the proof is just to count how many dots there are, because all of those are ordered pairs. Well, hopefully that's not too tricky, right? Because right here, we have n1 dots there. But we also have n1 dots here, and n1 dots there, and you can continue that, and we're going to have n1 dots in each of these rows. Well, the question is, how many rows are there? How many times am I adding n1? So we have n1 plus n1, and we're adding n1 a bunch of times. Well, the question is how many times? And the answer to that is n2 times, right? So we are adding a number n2 times, which by the definition of multiplication means that we're really multiplying this times n2. And that's what we wanted to show. Okay, so how is this useful? Well, it's actually incredibly useful because we can just immediately start counting. But let me just give you just a quick example of why this is useful. Example. So I have 10 shirts distinct shirts and maybe 6 shorts. And I want to know how many short outfits can I make? And the answer, well, just apply. That is not the word apply. Apply theorem 1.1 with n1 equaling 10 and n2 equaling 6. And then there are going to be 10 times 6 or 60 different outfits. Okay, hopefully that makes sense, right? So one shirt can go with any of the 6 shorts. And then the second shirt can go with another 6 shorts. And then the third shirt, another 6 shorts. So we're just adding 10 6 times, or we're adding 6 10 times. Either way, that's 10 times 6, which is 60. All right. But I wear more than shirts and shorts. I also have underwear and socks. So what happens when you have more than 2 groups of objects and you want to figure out the total number of possible combinations of maybe 5 elements? So instead of, say, an ordered pair, we might have an ordered triple, or an ordered four-uple, or a 5-tuple, or a 6-tuple. Well, we're going to have to generalize this theorem. Okay, and that's going to be theorem 1.2. Which is really the one that we're going to use. And it basically says, given n1 objects that we can enumerate kind of in the same way, maybe n2 objects here, and then this just continues on, right? Until finally, maybe our last one is going to be like nr objects, maybe x1 all the way to xn sub r. Then we can say there are exactly n1 times n2 times n3 times nr distinct r-tuples of the form AI, BJ, well, actually, let's do AI1, BI2, all the way to XIR. Okay, with, of course, I1 going from 1 to N1, I2 is going from 1 to N2, and IR is going from 1 to NR. Okay. We're not going to prove this. If you want to prove it, what you'll have to do is you'll have to use theorem 1.1 and mathematical induction, which I'm trying not to make a requirement for this class. So you can just generalize this theorem. And then instantly, if I have 10 shirts and 6 shorts and 20 pairs of underwear and 15 pairs of socks, you just multiply all the numbers to get the total combinations of an outfit of 4 items. Okay, so that's what this R tuple is, right? How many different objects do you want in a group? Then how many possible groups are there? Okay. Okay, so we can use this, and we can just do an example. So let's start our first example. Okay, example 1. What is the probability of getting 3 6s in a row or in a throw of 3 dice. Okay, so the solution, we're just going to use theorem 1.2, okay, where N1 basically is how many different possibilities are there for the first die that you throw. N2 is how many possibilities are there for the second die that you throw, and N3 is the third die. Well, they're all going to be the same in this case, right? So N1 is going to be the same as N2, which is the same as N3, and they're all 6. Okay, so then the total number of outcomes when you roll 3 dice, which we've labeled capital N before, is just 6. Well, it's N1 times N2 times N3, which is 6 times 6 times 6, or 6 cubed, which is 216. Okay, now that's capital N. So let's go ahead and define event A as getting 3 6s when you roll 3 dice. So then we want to figure out how many ways can this happen. And if we can do that, then the probability is just the ratio of those two things, right? It's the ratio of this to this. Well, how many ways can you roll 3 dice and get all 6s? Last time I checked, that can only happen in one way, right? So n sub a in this case is going to equal 1. Okay, and the only way that can happen is the 3-tuple or ordered triple 6, 6, and 6. Thus, we have that the probability of A happening is, remember that ratio, number of ways A can happen divided by the total number of outcomes. That's the theoretical probability. And we already found that N was given by 216. Right? And we already found that N sub A was 1. And that's our answer. So I wanted to carefully go through that example just to show you that you can do it. You can apply a theorem that we've talked about in here. And I think I'm going to stop here. In the next video, we're going to go through a couple more examples and possibly some more theorems. See you there.